language code, scan it from left to right, and identify the different tokens, update the symbol table appropriately, and pass the output of the scanner to the parser, which then tries to figure out this program structure. Remember, we mentioned syntax-directed translation, and we said that we can think of the parser as being the coordinator of the compiler. So it will try to build a structure, and of course, all programming languages have a logical start point. That this is the first token you must see if you're looking at a syntactically correct program. So it will start to ask for tokens from the scanner. The scanner will keep pushing what it is identifying, and the parser will start to build the tree. Okay, remember we said that we have single pass or multipass, and in a single pass we're able to do scanning, parsing, and semantic analysis, as well as intermediate code generation, because ultimately you want compilers that work very fast. They're able to compile pretty fast and convert your source code to object code in the shortest time possible. So it doesn't mean that now first the scanner has to finish and then now push everything to the parser. So the parser controls the compilation process when we talk about syntax-directed compilation. And this is exactly what we want to do. So as we go through this topic, I want you to start visualizing that you're going to be writing a scanner. It will be receiving some code in high-level language for some programming language. And you'll be writing a program that then is able to make sense to identify what are the tokens and give them the attributes as appropriate based on the grammar of that particular language, and store that in a symbol table, which then will be referenced by the parser. So this, of course, is a successful parse because the parser has been able to use all the tokens that have been identified. So this is an example of another construct. So another example from a high-level language. So in the same case, the scanner will receive this and start to process it from left to right and should identify the tokens. So in this case, it has identified token type do, which is a keyword, a square right square left square bracket, token 4, which is a keyword, a left square bracket, and equals, and then token new, and it has identified an integer constant with the value of 0. Okay. Then pass this to the parser, and in this case, the parser is not able to make sense of this, so that would yield a syntax error or a lexical error. Most probably a syntax error because all the tokens have been identified, but the sequence in which the tokens have been identified is not coinciding with the grammar construct. So in this case, the parser would not make sense and would have a syntax error generated. Okay, so we understand what the scanner is and what we're trying to do. So how do we scan a source file? Okay, so you said we are scanning from left to right. So of course you'll read character at a time. So read the W, you somehow have to figure out that I'm still reading the same thing. Maybe when you see white space, you figure out I have finished reading a certain token. And when you say we're ignoring the white space, is that we use it to demarcate between tokens. But we'll be seeing that that's not the case for all programming languages. So that's a token, and say, aha, I have seen that's a lexeme, and it matches the token keyword while. So what we've talked about that we have to distinguish between a token and a lexeme. So a lexeme is what we find in the actual source code, right? And this is what enables us to figure out what kind of token we have recognized. So the token is the enumerated type that represents the class of tokens for which this lexeme belongs to. Okay, so you can think of this as a logical entity that is part of the source code. So I hope by now the difference between a token and a lexeme is clear. The token is the type, and the lexeme is the actual instance. So here we are saying token while, and we've seen the lexeme while. So of course, for keywords, there's only a one-to-one matching for token. Well, there can only be one lexeme. But we'll see for tokens, like in the next example, there are tokens where a token can match multiple lexemes. So we've finished with well, then we continue that, we ignore that. Then sometimes we will discard a lexeme because in this case it is just white space rather than storing it for use. So in this case we're ignoring white space because it has no bearing on the meaning of the program. And I don't want to be doing this thing of admitting students. I've already posted the Meet link on the Google Classroom. So this is the last class where I'll admit people. You must log on to your Google Classroom and join because it's so disrupting for me to just keep having to switch to admit people into the classroom. So from next week, if you're not able to join, that's your problem. You're supposed to be on the Google Classroom and you join from there. So we talked about sometimes the white space, depending on, of course, the grammar of the language, we can ignore it, or if it bears meaning in terms of the semantics of the syntax, then you would record it. Then from there, we've seen another token. So that's a right bracket. It's matches a single lexeme. Then now we start seeing a numeric type of a token. So we continue scanning until we found a token of integer constant type. And the lexeme or the associated value is 137. And remember we said now this is what goes into the attributes in the symbol table for this particular token type of a constant and an integer constant. So we're saying some tokens can have attributes and that store extra information about the token. And here we make this entry into the symbol table. So you record, we have seen an integer constant and its value, which is an attribute now, is 137. So we're basically storing the integer which is represented by the particular token that we have found. So what are the goals of lexical analysis? So we said number one, and the most obvious one, is that the scanner must identify the tokens that are represented in a given source code. So convert from the physical description of a program into a sequence of tokens. Here, note we're saying that each token represents a logical piece of the source file, what we're calling an enumerated type. It could be a keyword, it could be the name of a variable, it could be an integer constant, it could be an operator, whatever it is. We need to know what it is and remember the token types are defined in the grammar of the language. Each token is associated with a lexeme. So for example, the actual text of the token is what we're referring to a lexeme. So for instance, we saw the integer constant, the value associated with it was 137, which is not the lexeme. Then some tokens may have optional attributes. And this information, which of course is going to be derived from the source code, is stored. A record of that is made into the symbol table. Then once we have the complete token sequence, this becomes the input to the parser, which will use that token stream to try and recover what is the program structure. Remember, the meaning of the program is derived from the syntax. So the first step is to recover the syntax, and then you're able to figure out what instructions or what action did the user intend for the computer to do. So now the biggest challenge when we're building the scanner is, of course, to determine what tokens and how do we match tokens to from the source code. How do we identify which tokens? We'll see there's a lot of ambiguity, and we'll see how to handle that. So in this case, the first question we are asking, if you're to find, if this becomes your input, if this is the source code, what are the important tokens? Of course, largely depending on the grammar, but if we look at this, which are the tokens that are useful? And useful here means bare meaning, especially for the subsequent phases. So could we just have people say out loud without putting up your hand, you just talk? What are the useful tokens that you'd expect to see if the scanner was going through this to generate useful tokens? You understand what the code is doing. So what do you think are the most important tokens?
All
4.
of the tokens excluding the white space.
Say that again. I didn't hear. Was it Craig who was talking? I didn't hear what you said.
4.
Okay, there's four. Thank you. Another one.
I said all of the tokens excluding white space.
Okay. So we have most of the tokens are useful. So you have the keywords, you have the int, you have the operators, and then of course we have the ones on this side are useful for syntax, but might not have an impact on the action. Of course, like less than would be there. Okay. Then we have the identifiers and the constant. Okay. So programming languages, how do you choose which are the good tokens? Of course, this is very dependent on the language that which you are building the compiler. And typically the standard practice is to give keywords their own tokens. So each keyword is going to be associated with its own token type. Then punctuation symbols will also have their own token types. We have lexemes that are grouped together for that can match more than one lexeme. So examples here, we have identifiers, we have numeric constants, we have strings, etc. And each of these form a different token type. And then after that, we may discard irrelevant information. So comments, white space, new lines, all those things. Yeah. So this is generally the standard practice for most programming languages. And so scanners follow more or less the same uh, rules. Now, one thing we'll appreciate, and you'll see these once you start building your scanners, is that it's not always very straightforward to come up to identify which is the right token to report. Okay, so let's look at some examples. So you may have heard of a programming language called Fortran, very useful many years back. Now, for Fortran, white space is irrelevant. That whether you write with white space or not, it means nothing to the Fortran compiler. So these are two examples of statements, and depending on how once you strip the white space, it could mean two very different things. So, for example, with white space, this could be a do statement. So, do statement 5 for I is 1 to 25, or it could be the name of an identifier. Do5I is assigned the value of 1.25. Okay, so you can imagine that this bit here is pretty hard because if white space is irrelevant, how do you determine which token to report? Are you going to report three tokens? One which is a keyword, one which is a statement number, and which is an identifier, or just one single identifier? So that becomes some of the challenges we might face as we build the scanner. So it can be difficult to tell when to partition the input. And you'll notice this a lot once you start working on scanning examples. The other one is that there's some programming languages which actually allow keywords to be reused as identifiers. So for example, PL1, which you can imagine how cumbersome that could be. So this is an example of a valid statement in PL1 because you're allowed to use keywords as identifiers. So for the scanner, trying to figure out is this particular instance, is this particular lexeme referring to a keyword or referring to an identifier? That becomes something pretty hard. So in this case, what is in blue are the lexemes which should be reported as keywords, and the rest are lexemes which should be reported as identifiers. So admittedly, you can see that this would be pretty hard for the scanner, and we need to ask ourselves then how do you build a scanner like UN for PL1 that is able to distinguish um, what token. So it might report both. It say I have two tokens, I have the same lexeme, could match a keyword or could match an identifier. And now it is the work of this parser to figure out based on what part where it's at in terms of passing the program. Was I expecting a keyword or was I expecting an identifier? And then use that information appropriately. That's why we're saying that the compiler phases are not independent. There's a lot of back and forth between the different phases to help in resolving ambiguities at different levels. Yeah, so in this case, we're saying it can be difficult to determine how to label the lexemes correctly because one of the most cardinal rules is that in PL1, for instance, is violated where the language allows using of keywords as identifiers. It's quite rare, but it is possible. So imagine if I give you a task to build a scanner for PL1, you'd have to grapple with this kind of a problem. So there are three main challenges that we'd have to think about as we embark on building or understanding how scanning works and how to build robust scanners. So the first question we have to address is how do we determine which lexemes are associated with each token? And we've seen the examples before. How do you determine how to partition a given lexeme into the appropriate and correct tokens? So the example for the do5i, are those three lexemes or is it one? Okay, so that's a big challenge. How do we accurately determine the lexemes that are associated with each token? Then the other challenge is how do we know which option to pick when we have uh, options in terms of how we can scan the input? So this is dealing with ambiguity. When we have an ambiguous result, how do we determine which one is the correct one to pick? And of course, as with everything to do with the compiler, we are very concerned with efficiency. When we did the automata course, we said we were concerned with possibility, but not efficiency. That we didn't care whether the thing that we were trying to do was being done efficiently. We only cared that it was possible to be done automatically. Now, when you come to the compiler design, of course, efficiency is of the essence. So it's not about just can it be done, but what is the best way to do it in the quickest and most accurate way, in the most efficient way. So there's a lot of research or algorithms that are put forward to help address the concerns of efficiency. So let's look at the first challenge, which is associating lexemes with tokens. So tokens give us a way to categorize lexemes by the information that they provide. Some tokens, as you said, may be associated with only a single lexeme. So in most programming languages, you find keywords are just associated with specific lexemes. So if you have keyword if, anytime you find if, you expect it to only match token if. Okay, of course, with the exception of a language like PL1. But we know that there's some tokens which might be associated with different types of lexemes or different lots of lexemes. So for example, variable names. So if you have token identifier, you can have an infinite number of identifier names. The same thing with token integer, the integer constant. We know that you can have an infinite number of possible lexemes where any number can be represented as a lexeme for the token type integer constant. The same thing with strings. So here what we're saying is that there are some tokens where there's a single match, so it's not a problem to identify that. But then because of these other different token types where there are so many possible options, then we need to think of a good way to identify and to efficiently know how to associate a lexeme with the correct token type. So we'll be looking at examples as we go along. So the sets of lexemes that can be, especially now for this second group where you can have many different lexemes associated with a certain token type, we think of now the set of lexemes per token type as a set, okay? So associate a set of lexemes with each token. For example, with the number token, we can associate it with a set of numbers. So if with the integer tokens, and we're talking about the set of positive and negative integers, for example. If you're talking about the token type string, then we need to associate it with a string of with a set that has any possible string that could ever be formed in that language. And for the simple token types, which are one-to-one, so for example, the token for the keyword well will also associate it with a set, but this would be a singleton that just have the one lexeme that we expect. So what we're saying is that as we start thinking about building our scanners, understand that for each token, there is a set of possible lexemes associated with it. For some token types, the set will be a singleton. For other token types, it could be an infinite, a set of infinite numbers. For instance, a set of strings, set of numbers, set of identifiers, etc. And of course, you remember that before we can even come up with a set, there must be the alphabet which has been specified for that language, so that we know that even as we're defining these sets, the only valid lexemes must be built up from the alphabet of that particular language. So there's that kind of bounding. So how do we describe which set of lexemes is associated with each token type? So in other words, let's take the example of, for instance, the number token, the token type number. How would we describe the set of possible lexemes that can be associated with that number? Let's hear your ideas. We're saying we have sets, and sets have some are infinite membership for different token types. So what are the possible ways that we can describe these sets? And somebody hand up or what? Yes, Taylor.
You could define a grammar like similar how you did to automata, where you just like define some letters and then you say anything built from this would be valid in that set.
Mm-hmm. Yeah, thanks. So exactly, we need to find a formal description for those sets so that we know exactly the boundary. And so that description could be a grammar, it could be a certain language. And this brings us to in fact, what Taylor has just talked about, what we did in Automata. We talked about formal languages. And if you remember what we said, a formal language is just a set of strings, okay? So the sets we are associating with a token type is basically a formal language. So we have the language of integers, we have the language of identifiers, we have the language of strings, we have the language of certain token, like token while, etc. And we're saying that for most of these languages, they may be infinite. So even if they are infinite, they have finite descriptions. So we can define the language using an automaton or a grammar or a regular expression. Okay. And we can use these descriptions to then define the set of strings that are associated with a particular token type. So this set of strings are the lexemes for a given token type. So we'll be using all of these approaches, and we'll see how, like regular expressions, the regular languages are what we use to describe the set of lexemes. And then when we go to the parser, we'll be using context-free grammars, like the one I gave you for Pascal, to represent the structure of the language. So just a recap or a refresher on what we did in Automata. So I hope you all remember what regular expressions are. I hope you remember the properties of regular languages. And if you don't, you're well advised to quickly scan through what we did when we did regular languages. So regular expressions are a family of descriptions that can be used to capture regular languages. Okay, and they provide a compact and human readable description of these kind of languages. And there are many tools that can be used to build scanners, and one common one is known as the Flex tool, and there are many other. They're called lexical generators, lex generators. I may not require that you use these tools. In fact, I prefer that we build our scanners from the ground up. But if as a team you think you're better off using a scanner generator, I have no problem with that, as long as we've understood the concepts behind it. That first, there's a token type. It has associated set of lexemes. We represent that set of lexemes. We think of it as a formal language, and there's a mathematical description or a compact description of that language. And that description could be implemented either as an automaton or as a regular expression. And then now we write code either by hand that implements that regular expression or the automaton, or use a tool that is going to take as input your regular expression, the description of your lexemes. Okay. So just as a refresher on regular expressions, so we did this. So I'm sure at least you won't be able to say, no, we didn't do that. I taught you, so I know that we did it. So remember, we have different types of regular expressions. We have atomic regular expressions. So lambda is what represents the empty string. So here we're using epsilon, but remember you can express lambda using just the lambda notation, or some other books use the epsilon to represent the empty string. So it doesn't really matter as long as you're consistent. And then the other atomic regular expression is that represents a single symbol. So for instance, if you have the letter of the alphabet A, that's a symbol, then the corresponding regular expression is just the same symbol. So those are for atomic regular expressions. Then we have the compound regular expressions. And we did a lot of this, where we said the operations that we can perform on regular expressions. So we can use operators such as concatenation. We can use operators such as the union or the clean closure, and apply that to a regular expression. Okay. So if you remember this, that if R1 and R2 are regular expressions, then R1, R2 is also a regular expression which expresses the concatenation of the two languages. So R1 is a regular expression defining the language R1, and R2 is a regular expression that defines language R2. If you concatenate those two regular expressions, then the result is actually gives you the concatenations of R1 and R2. And I hope you remember what that means, is that the first part of the word would be coming from language L1, and the second part of the concatenated word would be coming from R2. And then we have the union. So using the union operator. So there we also did, I think we also used the either or. So either R1 or R2. So we use the plus, but the same notation, you can just use the bar to mean union. So this represents the union of R1 and R2. Then we came across the clean closure, and we said that we use the clean closure to form an infinite language from a finite language, or even to just extend the membership of an infinite language, as long as, and remember that the clean closure includes lambda and all the members of the set for which we're taking the closure. And if R is a regular expression, then whether we put it into brackets, we've not modified the meaning. So R, the brackets really are just to help us group the different terms of the regular expression, but they do not change the membership of our sets. So we have atomic regular expressions and we have compound regular expressions. So this is just kind of a recap. Then one thing we didn't mention then, which we now must talk about because we are talking about implementing an actual compiler, is the notion of operator precedence. So this is the precedence that is given to regular expressions. So of course, the parenthesis comes first, then the clean closure, then concatenation, and then union. So for example, if you get a regular expression as shown there, so A, B star C, union D would first then take the precedence, which is the clean closure. So we have B star, and then we concatenate it. And then remember, there's left associative and right associative operators. We'll be talking about that in detail. So in this case, the operand associates to the left. So we have A, B star. And then From there, we have the C, AB star C, and then finally we have union D. Okay, so note that there is the issue now of operator precedence as we're trying to figure out how to express our sets. Now, I hope we remember regular expressions. So supposing our alphabet sigma has two characters or symbols, 0 and 1. This is an example of a regular expression for strings containing 0, 0 as a substring, right? So we are saying we have the mandatory part, which is the 0, 0. Before it, we can have 0 or more combinations of 0 or 1. And after it, we can have 0 more combinations of either 0 or a 1 star. Okay, so I hope this is stuff that you remember. And if we just shade for different colors, we have different colors for the different parts of the regular expression. Supposing these are now the inputs that we have a string from this language that is represented by this regular expression, we can already see what part of the regular expression matches what part of the string, okay? So in this case, for the first one, we have a 0, 0 matches here. Then we know that anything to the left of 0, 0 must be matched by this regular expression. And anything to the right is then going to be matched by this part of the regular expression. Okay. So I hope that is clear. So can somebody give us that regular expression for strings of length exactly 4 over 0, 1? Let me create a Jamboard, then we just start using that. I hope I still remember how to do that. Yeah, then a Jamboard. So I hope you have access to the Jamboard. So I'd want somebody to give us that regular expression. So the regular expression is here. So over the alphabet 0, 1, we want a regular expression for strings that have a length of exactly 4. Are you able to access the Jamboard? Okay, can somebody give us that as a refresher? Yes, Taylor, go ahead and write it on the Jamboard. I don't understand what's going on.
I can't type into the Jamboard.
Huh?
I can't type into the Jamboard.
I thought I gave all of you edit rights. Is anyone able to type? Oh, sorry, I see what I didn't do. Let me make everybody an editor. So just try now. Tell, are you able to type now?
It's giving me a bit of trouble as of now. So let someone else answer, and then I'll answer another question.
Okay, let's have somebody else volunteer to do that. Who is that? Can just go ahead. Yes, Kaiser.
I've typed it on the chat.
Oh, on the chat. Okay. Also, Adrian had typed that. Okay. Yeah, that looks correct because we're basically saying for each of the 4 positions, you're choosing either a 0 or a 1. Okay. So that is our regular expression for strings of length exactly 4. So the same way, if we have a string of length 4, we're able to show that this first regular expression gives us the first character, the one in purple, the second character, the one in that color, the third, and the one in gray, the fourth. So this is another way of expressing it. So of course, this is how we learned them. But as you start implementing and even you start using regular expressions in other languages, you realize the syntax differs. So you can actually just say 0 or 1 4 times. That's a different representation. And we'll do the same thing. So let's have somebody else give us that, either write on the Jamboard, or I prefer if you can write on the Jamboard to give us that regular expression.
Excuse me.
Yes.
I don't think any of us have access to the Jamboard because I've tried multiple times and it's saying we're sorry, you don't have access to the Jam.
That is so weird because, but okay.
If you access it without your school email, it will allow you access.
Without the school email.
Yeah.
That is so weird.
I use that general access link. So if you use an school email, it will allow you to edit into it.
Thanks. Let me try that.
Okay.
Oh, that's weird. So I hope somebody is giving us the. Can we see it now to keep shifting different windows? Strings that contain at most 1 0. Who's doing that one for us? We just want a regular expression. Yes, Jerry?
Okay, let me do it on the Jamboard.
You can use the text, whatever, Jerry, and type. You can use the text icon.
Okay.
Are you typing, Jerry? We can't see anything.
Yeah, I'm typing.
Okay.
I'm done.
Okay. So lambda or 0, either lambda or 0, 1 star. Okay, are we happy with that?
Can I make amendments?
Yes, Craig?
Let Jerry make amendments, then I'll talk out.
All right.
Okay, I'm done now.
Yeah, that is correct. So we're saying it's 1 star. Then we choose between 0 or lambda or 1 star. Is everybody happy with that?
Yes.
That is quite correct. Okay. Which is what Jerry has written for us. And as before, we are then able to show which part of the token, the lexeme, matches which part of the regular expression. So that's another way of expressing either or. So it's the same way. So all these are different, those are different expression for the same regular expression. Now, how do we apply regular languages now to the problem we want? Because we've done regular languages, we've understood regular expressions. We now want to use that as a description for the programming languages for which we want to build a compiler. So for every language, you start by defining the alphabet. So for example, if you think about most of our programming languages, we suppose that the alphabet for those languages is all the ASCII characters. So a regular expression based on ASCII for the even numbers would be, we're basically saying if they're both positive or negative or unsigned, we'll do something like that. And then you're choosing either of this, 0 or more times, but the ending must either be a 0, a 2, a 4, a 6, or an 8. Okay. So this is a regular expression for even numbers. Have I gone backwards? Yeah, and this would generate for us this kind of, we can have unsigned integers or those that are plus or minus, etc., as long as they end with an even number. So while we're doing this, remember we're trying to explain. Is there somebody asking a question or what? It's so annoying for me. Did somebody raise their hand? Or not?
Sorry, that was accidental.
Okay, sure. All right. So remember, we're trying to do this because we're saying for our token types, especially those that match multiple lexemes, we need a way to define the languages, a language for that token type, such that we're able to identify any given lexeme for that token. So it could be the language of integers, the language of identifiers, the language of strings, etc. That's what we're trying to do. And we're saying we can use regular expressions for that. So we just need to remember how to define regular expressions. So once we define the regular expressions, the next thing now is to implement them and use them to match our lexemes to the token type. How do we implement regular expressions? So we never implemented them. What we did then was just learn how to define them and use them to make decisions or proofs about the sets we were defining. So now we're talking about implementation. So we can implement regular expressions using FAs, finite automata. And you remember there were two kinds of finite automata. We had the non-deterministic FAs and we had the DFAs, the deterministic FAs. So I want somebody to remind us what was the difference between the two types of automata. What was the difference between DFAs and NFAs? Yes, Adrian.
For DFAs, every input has a specific output, and that output doesn't change. While for NFAs, an input can have every input has a set output, and the output doesn't change. While for NFAs, and it also has one output for every input.
Adrian, what do you mean by an output? Did the FAs have any output? We only talked about the more which had output.
One path.
Okay, now say it again so that we understand the difference.
Okay, for DFAs, every input or character has one path, one specified path, and that path doesn't change. For NFAs, an input can have multiple paths.
Yeah.
Yeah.
Exactly. So just as the name suggests, deterministic means that for a given sequence of characters, there's only one single path through the FA to an accept state. But for NFAs, we have a choice, right? And remember, we said that for a DFA, from every state, for every letter of the alphabet, there was a single transition. But for NFAs, you could have 0 or more transitions from the same alphabet letter on a given state. And that was what was bringing the non-determinism. Okay. So we've already seen this regular expression. So what I would want on what I would want us to do, I think I'm going backwards. I'm going to use my arrow keys. They're taking me to the wrong place. So I'm sorry about this. I think there's something wrong with my machine today. So I won't use the arrow keys. So let's look at some of the automatons. So can somebody tell us what language, or even write for us the regular expression for the language that is accepted by that automaton? So first tell us, is this a DFA or an NFA? And tell us what language it is representing. You can answer, whoever has raised their hand. I don't keep flipping to the other tab.
I think it's an NFA. Sorry, it's a transition. Oh my God. It has empty strings.
Does it have empty strings? That's a quotation mark.
Okay, then it's an NFA. Yeah, that describes the language of quotations.
The language of quotations, which one is that? The language of?
So any letters in between two quotation marks, just as Greg has highlighted in the chat. Craig, sorry. Yeah.
Greg has already given us the regular expression. We're basically saying it must start with an open quote and then choose, is it a 0 star? 0, is that a clean? Let's see. Yeah. So it can actually accept the null string that has no characters, or one or more repetitions of the letters A to Z, and then finally terminate with a closing quote mark. Okay, thank you. So that's a simple automaton. So for those of us who've forgotten, we had states, we had transitions, and we denoted the states using nodes. And the automaton's configuration is determined by the state that it is in. Okay, so now this is going to give us a chance to actually implement FAs and see how useful they are at the stage of implementing scanners. Then we had the transitions that showed how the machine changes state from one state to another by consuming a particular input. So this is an example of an input that could be run on this machine here. And we expect, of course, the automaton will take this string as input and decide whether to either accept or reject the string. Yeah, remember there were no outputs unless we were doing the FA with output, which are the Mealy machines or the Moore machines. So the simple automaton basically just give a decision. If the string, you have consumed the entire string and the machine has terminated in a final state, then we say that string is accepted or it is rejected if that doesn't happen. So in this case, we start with, and remember we process the strings from left to right as we're operating on the FA. So from the start state, consume the quote, transition from the start state to the middle state. Then read an H, remain there, read an E, loop back, read a Y, loop back, read an A, loop back, read the quote, transition to an accepting state. The entire string has been processed. The machine is in an accepting state. So we can say that this string is valid. So I hope you start to see the correlation between now our FAs and how we can use them to determine whether we have seen a valid token, a valid lexeme for a given token type. Okay. So remember we had the double circle indicating the accepting states. So anytime the machine ends in that accepting state, we say that the string has been accepted. So this is really just a refresher for us. What happens if we put this as the input? So we'll note that we expect this to, will this fail or will this be accepted or rejected?
Rejected.
Yeah, we expect that it should be rejected because our FA just allows two quotation marks at the beginning and at the end of the string. So that will transition there. Then on the second quote, we transition to the final state. And then we read that there are no transitions from the final state. We've not consumed all the input, so that should end in a reject. There's no transition on quote, so the automaton crashes and rejects that input. So the same thing is an example of another string that should be rejected. And I hope now you start to see how this becomes a very useful tool to check for valid lexemes to be able to identify token types. So this is an example of an FA that is accepting for us tokens of type string. Okay. So any input that you run on that machine that ends in an accept state and you have somehow figured out the end part of the token of the lexeme, then you're able to say, aha, we have seen a token of type string. So in this case, we'll expect that it will reject because we don't have the final quote mark. So it's not an accepting state. The machine has consumed all the input. It's not on an accepting state, so it rejects. Okay. So let's look at a more complex automaton. Who can tell us what is happening here?
Can I speak?
Yes, please.
I think it's an NFA, and so there are two approaches. So the first one should, the first state after starting, you can loop around either 0 or 1, and then the next transition is a 0, following with a 1, and following with a 0, and that ends with an acceptance state. And then for the second approach, you can loop through a 0 or 1 however many times, and then the next transition is a 1, a 0, and then a 1, following an accepting state.
Okay. Thank you. So what would be the regular expression corresponding to the language that is accepted by this NFA?
I think it's a language that can contain any number of zeros or ones, but it has to end in 010, or I think it was 101.
So do you want to write that down? Want to see, or Tevin has written it for us.
Yeah.
01 star, then the ending should be 101, either 101 or 010. Okay. And the rest of you who are so quiet, I can't just have like 6 students and then ones who are active in the class. The rest of you are just quiet. So this is an NFA. There are multiple transitions defined from a given state. So on a 0 and a 1, you could either loop in this start state or transition here. The same thing with the 1. And our machine now has multiple final states. So either if the machine ends here or it ends here, it is accepting. So these are more complex automatons. So if this is the input we are presenting to it, we can see what would happen. I'll just quickly go through that. Sorry, let's go back and discuss what is going on. So we present and then read the first from the start state, read a 0. So we have 2 options here, right? So you could either loop or transition to that first state. Then read a 1, because remember now with an NFA, you have to explore all the possible paths. You can't just take one and assume that's the one that can accept the string. So you have to explore multiple paths. Then from there, we read a 1. So from the first state, you would transition here. If we're in this state, we transition there. Then read the 1. What happens here? That doesn't work. Read another 1. Doesn't work. Read a 0. Then finally the 1. And we've ended in at least one accept state. So that is accepted. Yeah, since we're in at least one accepting state, the automaton accepts. So remember we said that the NFA is easier to represent a language, but harder to determine whether a string is accepted or rejected. The DFA was different. Harder to construct, but always easy to determine whether acceptance or rejection because there's only one unique path through the machine. So it was a trade-off. So this is a TG because it allows epsilon transitions. If you remember, we had the lambda transitions. And easier also to represent the language, but harder to process whether a string is accepted or rejected. So we have the lambda transitions, and these are followed automatically without consuming any input. So if you have something like this from the start state, you can be in any of the 3 start states. Then you can consume a B, consume a C, a C, a B, and D, and A, and accept. Okay. So I need you, if you've forgotten about FAs, that you're going to go read up and make sure you remember. I think I'd given you also an assignment. Part of your reading from last week's class was on subset construction, how we convert from a DFA to an NFA and vice versa. Very, very important because we'll be seeing as we define the languages for our token types, we may need to move between regular expressions, NFAs, and DFAs. So you need to be able to comfortably move from one representation to the other. So simulating an NFA, when we have multiple paths to take, we must keep track of a set of states. Initially, the start state, and then everything reachable by the lambda moves. So for each character in the input, we are going to maintain a set of next possible states. Of course, as you're starting from the start state, it's going to be initially empty. But for every character that you read, you have to simulate the possibilities based on the way the network has been drawn. And then you add these states to the set of new states. And then the next time you consume, you're going to go from the set of next states and make another transition and update the possible set of new states. So you add every state that is reachable by a lambda move to the set of next states. So the complexity of an NFA is of the order n squared, where the string is of length m, and we have an automaton with n states. Yeah? So you can see the number of states. So the complexity increases with the number of states. And remember, we're saying for the compiler, we're very interested in efficiency. So anything that we can do to reduce the complexity and the time taken to make a decision whether a lexeme is right or wrong is something we need to be very conscious about. How do we then convert from our regular expressions to NFAs? Because we said we're going to represent the formal languages representing our lexemes or token types using regular expressions. Then now want to convert our regular expressions to finite automatons, okay? So there is a procedure to convert a regular expression to an NFA, and we did this in year 2, so you already know how to do that. So you want to associate each regular expression with an NFA respecting the following properties. There must be exactly one accepting state. So remember, the NFA can only have one accepting state. There should be no transitions out of the accepting state, and there should be no transitions into the starting state. So you should not have a loop back to the starting state. Yeah. So these restrictions are hard, but they make it easy, especially when we now have to use these NFAs to make decisions about the lexemes and which tokens to associate them from. So you're basically saying you're going to ensure there's only one start state and there are no transitions into the start state. There's only one accepting state and there are no transitions out of the accepting state. Okay. So let's look at the base cases. So if you start with an automaton for lambda, basically accepts only the null string, it would look like that. And then the one for a single character, basically from the start state with that character, you go to an accepting state. Then now we use this to build onto everything else. Now, do you remember how we did this? Because we showed you how to concatenate two automatons. Who can remind us what we did? Or how would you construct the FA that is the concatenation of two regular expressions?
I can attempt
Okay.
on hazy knowledge, but I recall that we spoke about, since it's a concatenation, we should first build the finite automaton to read the initial part of the input string that accepts the first part of a regular expression.
Yeah.
And then for the rest of the finite automaton, we should build components that allow transition to the next, that accept the next part, accept or reject the next part of the string that's yet to be completed.
And how do you do the concatenation?
Via transitions. Or
On what?
yeah, I don't remember exactly, but I just remember the whole splitting string.
Okay, thank you, Aduma. Yeah. So basically, we're just doing it pictorially. We have two regular expressions. So of course, each of these regular expressions is representing a regular language. So if this is the regular expression for R1, it has a start state, it has an accepting state. And then of course, you have all the many nodes as needed. And then we have the same thing for R2. So when we want to concatenate this, what do we do? So we need to get rid of this start state because now we are trying to do the join over here, okay? And we replace that with a lambda transition so that you can jump from this final state to this start state without consuming any input. And change that from being an accepting state because we only want one accepting state. So you start here, reach here, jump to the next start state, and then complete on the final state of the second machine. Yeah, so that should have reminded you. Now, when we want to do either R1 or R2, how would we do that? Craig, how would we, could you explain to us just generally, how are we unioning two machines?
Generally, their start points for both R1 and R2. They'll share a start point and they'll share an end point. But I
Yeah.
can't remember the details in between.
Okay, but at least you remember something. That's good. So we have either R1 or R2. So we have the two machines. So we have the machine accepting the language defined by R1 and a machine accepting the language defined by R2. Both have their own start points and end points. So what we want to do, as Craig says, is create a common start state. And then, of course, you're going to transition on a lambda to the old start states. And then we want to create a common final state, the same thing. Introduce a final state and have a lambda transition to the common start final state, so that we are obeying the rules that we've said. There should be one start state, one final state, no transition from the start state, and no transition into the start state. And that gives us the union of two regular expressions expressed as an NFA. Now, for R star, so for R star,
Single acceptance.
okay, go ahead. Yeah, so we have the single language. We have the machine accepting R. How do you do R star? Yes, and go ahead. Yes, who was that? Yes, Craig.
Yeah, I think for R star, since it accepts the null, which means that the start state can also be an accepting state. And then, yeah, that's all I can say.
Okay. So in this case, we're going to introduce a new start state and a new final state. Then we're going to have, because remember, R star should accept lambda because it's a clean closure. So we'd have a transition from the start state to the final state on lambda to cater for the star, the lambda. And then again, a lambda transition to the old start state and a lambda transition from the old final state. And because we don't want to, we have to do the recursion for clean star. So we'll recurse inside there. And you see, we're doing it this way so that we don't have a transition into the start state. Yeah, so you just transition over there on lambda. And that becomes how we translate the R star regular expression into an NFA. Okay. So you need to go back to your year 2 notes, read through, refresh your minds on regular languages, read through FAs, DFAs, NFAs, and all these things, the concatenation, the union, and the clean star operator of regular expressions and how we translate that into NFAs. Okay. So we've looked at the first challenge in scanning, that we need a way to determine which lexemes are associated with each token. And we've introduced the notion of using formal languages to do that. And then for those formal languages, we are going to describe them using regular expressions, which we implement as finite automata. Okay. So the first is what we're going to be doing. So I think I want us to stop here. But just as a teaser, the first challenge we'll face is now when we're trying to determine which lexemes to associate with each token. The first thing we're going to come across are the lexical ambiguities. So this is a good example. So in the grammar, we could have token 4, where 4 is a keyword, and it matches this lexeme as given, FOR. Then we have token identifier. In fact, the biggest ambiguities are between keywords and identifiers. So we can have a token identifier, which is represented using this regular expression. So you have capital letters A to Z, including underscore. That's how you start the identifier. followed by 0 more repetitions of capital letters, small letters, and digits and the underscore. So that's actually a regular expression for the token type identifier for most programming languages. Okay. So why is this a challenge? Let's take a look at what this would look like, although we're going to stop shortly. Supposing this is what is in the user's program, FORT. So our scanner needs to figure out, am I seeing token 4 and identifier T? Or am I seeing identifier FORT? Or am I seeing identifier FOR and another identifier T? So you can see all the possible ambiguities that you can have. That it could be you're seeing one identifier FORT, or you're seeing the keyword FOR and an identifier T, or you're seeing a keyword FOR and identifier FOR and an identifier T, of course, depending on the language, or 2 identifiers FO and RT, or 3 identifiers FOR and T, or FORT. You can basically see that your scanner now has to figure out what lexeme to match with the token that you have. And that's actually the bigger chunk of the work that the scanner has to do in terms of identifying as the first challenge. So we're going to stop here and we'll continue with this, looking at the possible approaches that we can use to resolve lexical ambiguities, such that as you implement your scanner, you don't run into this kind of a problem, that when you find something like this, that the rules that are used to break the tie, do we prefer to report first, identify the keywords, or what rules? There are many different approaches. So we're going to look at those in the next class. So for now, we're going to stop here, and I'll ask that you go read up on DFAs, NFAs, regular languages, regular expressions, because those are the tools you're going to use for your scanner. So the next steps, I will post the work that you're going to do tomorrow. And the first thing we're going to do is, in your groups, you're not going to do some research in terms of the programming language you want to build a mini compiler for. I'm going to post, I'm just explaining the work you're going to do tomorrow. So the first thing is you have your groups. The first decision you make as a group is the programming language you're going to work on. So here you can create your own. I just call it a mini language because I don't expect you to build a complete compiler because of time, but want to at least ensure you can do a scanner, you can do a parser, and you can generate some intermediate code. That should be the objective for the course. And to do that, of course, the first thing, you must have a grammar for some language. So you can make up your own grammar from scratch, or rather your own programming language that has its own grammar, or you can take an existing programming language and strip off a lot of the stuff. So just keep it really simple so that you have a mini version of an existing programming language. So you can borrow some rules maybe for statements, for identifiers, etc. I will specify what it must be in your language at a minimum, so that you don't come to me and say, oh, my language can only have one identifier or one keyword. We don't want it, again, to be so simplistic that we are not able to learn some of the challenges and see how we overcome them. So that's the first decision. You must come up with a mini language and its associated mini grammar. And then from there, the next decision you'll have to make, we see we already started looking at how to implement the scanners, and we're saying we represent the tokens as regular languages, which using regular expressions. And you can see that this is a regular expression actually. So you're going to do something like this, that these are my tokens in my language. And for each token, you're specifying a regular expression for it. So token identifier, I'm sure for most programming languages, will just look like this. So you're going to have your list of tokens over here, and the corresponding regular expressions. And then from there, the next decision we're going to make is that now you have to implement, you're going to come up with a DFA or an NFA that you're going to translate your regular expression into an automaton. Yeah. You can translate it into an NFA and then into a DFA. An NFA is easier to implement but harder to make decisions with. A DFA is harder to implement but very quick to make the decisions with. So you're going to do a research and justify your choice. Where am I using an NFA? Where am I using a DFA? And that's why I said you need to learn how to translate from a DFA to an NFA and vice versa. Okay. So that's the next thing you're going to do is determine. You're not going to do a lot of reading actually around implementation of scanners. Note I mentioned that we can have, there are tools to help us generate scanners. Yeah, so Flex is one such tool and there are others, okay? You're going to then decide as a group, you're going to read up and look at the pros and cons of using a scanner generator or building your scanner from scratch. And then you make a decision. Are we going to build using a tool? Of course, when you look at the tool, you have to go look at how to specify it, how to run it, how to compile it, the steep learning curve, if there's any, etc., etc. Or simply say, we're going to implement everything by hand and then choose as a team the programming language you're going to use. I think somebody asked me this last time. I'm agnostic in terms of the language. For me, I just want to see that you've implemented a scanner. That if we push source code based on your grammar to your scanner, it can generate for us the tokens and we can see what has been written into your symbol table with all the attributes needed. Okay. So that is the other thing you'll have to do is make a decision. Are we going to use a scanner generator or we're going to build by from scratch? So that would be the work for tomorrow, is reading up to understand what it takes to start building your scanner. Even before now, we have the next class where we talk about, in fact, maybe tomorrow's class. I'll confirm whether we'll have a class tomorrow so that maybe we finish. I think actually that's what we should do. Just give me a second. I just confirm something. Because we may even just have a 1 hour class so that we finish on this bit of handling ambiguities. And then you go into your discussion groups and you can start working over the week before now, the next class. Let me just check something for tomorrow. We're supposed to meet at 2 p.m., right? Yeah, so tomorrow we'll have the class between 2 and 3 p.m. so that we finish today's topic. And you'll be well on your way now to start doing the scanning project. So word of caution here. In the past, there's student teams that have opted to use scanner generators, thinking it's easier. And it didn't go very well. Because it's a whole new programming language, you have to be really good at specifying the regular expressions and then converting it into the format of that tool. If you do it well, it generates it's quite straightforward. But just a word of caution, the people who end up moving along very fast are those who build it from scratch. Yeah. So have that discussion in your groups and make sure that as you're choosing to use a scanner generator, you've spent a lot of time trying to play around with it to understand what will be needed for you to do that. Okay. So let's meet tomorrow at 2. And then everything I've described today, now you'll continue to work on it after the class and into the week. Those of you who haven't joined Google Classroom, please make sure you do that because I don't want to be spammed with many emails of assignments being submitted via email. That is the quickest answer, quickest way for you to lose marks when I can't trace your work on my emails. Can you imagine I'm teaching many other classes? So try and just submit your work on Google Classroom. Do you have any questions?
We've submitted a link to a spreadsheet with emails that don't have access to the classroom.
You shared that with me via email?
It's on chat. Yeah.
Are your names in the class list shared by the administrator? Because all I'm doing is just taking cut and paste from the official class. You can see my screen.
Yeah.
So I come here, year 3, group 1, I just copy all these emails. And I say, so if your email is not here, I cannot add you. Those are the rules of the university. If your email is here and it's been added by the admin, I can add you. Yeah. So if your emails are not here, what you should be doing is quickly just going to the admin to make sure that they have not forgotten to add you onto this group. We have all the classes for the entire school.
Okay.
Yeah, so I think that's what I'm not getting, why these emails are not there. So if your list is there, please see the admin. Okay.
Sasa.
But the good thing is that I don't think there's a group where nobody is in the classroom. Going forward, you're doing group work, we'll be submitting a group. So I hope at least there's a member of each group who is on classroom for now to submit on the behalf of the group. Any other questions? Yes, Edith? Edith, I can't hear you.
Will you upload
What? I
I'm
think Edith just,
asking if you will upload the notes
yes,
for
yes,
this lecture.
yes, I'll do that. I'll do that. Any other question?